Thank you for the introduction and the invitation to speak here. It's my first time in India, and it's been great so far. Yeah, so I'm going to talk about non-Hermitian random matrices. So I think the best place to start is just with the simplest non-Hermitian random matrix you can think of. You just take an n by n matrix and let every entry be a random variable independently with the same distribution. And we'll assume it has 0 mean, and I'll normalize it so that the variance of every entry is 1 over n. And then what we're interested in is what are the eigenvalues this matrix look like. So in order to study this, we define the empirical spectral measure, just be placing a delta mass at each of the eigenvalues with weight 1 over n. So here's a picture of what you get when you do that. So I took a 1,000 by 1,000 matrix, made all the entries random, 0 mean, and variance 1 over n. And you can see they're basically uniformly distributed on a disk, and if you look real closely, the radius of the disk is 1. And that's exactly the contents of the circular law, which was first studied by Gurko in the 80s, and there were sort of some numerous issues that had to be dealt with that we saw in the first talk, namely about the least singular value and these sorts of problems. And this was sort of started to be fixed by Bai in the 90s, and then there was sort of a lot of work, sort of culminating with Tao and Vu maybe 6 or 7 years ago now, and then since then there's even been strengthenings of this. But the basic law says that under the minimal assumptions that you have 0 mean and variance 1 over n, that this sequence of random measures of the eigenvalues is going to converge weakly almost surely to a deterministic measure known as the circular law, which is just the uniform law on the unit disk. So to put that another way, you can think of taking some test function f and then integrate it against this empirical spectral measure, which is the exact same thing as taking the trace of f applied to your matrix. And then this is going to converge in the limit to just the integral of my test function against the uniform measure on the unit disk. So in this talk, we're going to be interested in sort of a variation of this. So we're going to take the trace, and now I'm going to take two functions, f and g. So I'm going to apply f to my matrix x, and then g to the adjoint of x. And then we're going to consider just analytic test functions f and g. And this sort of problem was first considered by CochranMelech in the physics literature. I'll say more later about what they did exactly. So I have sort of two motivations for looking at this type of problem. The first one I think is a very interesting problem. I can't really say anything about it, but very recently there's been some work, and hopefully in the future lots more progress is made. And then the second problem I can sort of say a bit more about. So since I have non-Hermitian random matrices, you have to consider the right eigenvectors and the left eigenvectors, and also the eigenvectors won't be orthogonal. So you can sort of ask how not orthogonal are these eigenvectors. So the way to consider this problem is to take the left and right eigenvectors and then normalize them. So if I take the transpose of my left eigenvectors and multiply it by a right eigenvector, I get just 0, 1, depending on if I take eigenvectors corresponding to the same eigenvalue or different eigenvalues. Okay. So this choice doesn't actually completely define my normalization. So for example, I can take all the left eigenvectors and multiply them by some constant. And then if I multiply all the right eigenvectors by 1 over that constant, this relationship will still be preserved. So when we want to talk about eigenvector overlaps, it's natural to consider the left eigenvectors and the right eigenvectors together. So I'm defining the overlaps should just be, you take the overlap between the I eigenvector and the jth eigenvector. I take the inner product of a left eigenvector with another left eigenvector, and then multiply that by the inner product of a right eigenvector with another right eigenvector. Taking these left and right eigenvectors together preserves this sort of invariance. So if you define these eigenvector overlaps, then this quantity I'm interested in, namely the trace of a function of my random matrix times a function of its adjoint, can be written as this sum, or you can think of it as an integral against empirical spectral measures with now these weights added in. So either understanding eigenvector overlaps can help you understand this quantity, or understanding this quantity can help us understand the eigenvector overlaps. Both of them in general seem to be rather hard problems. So this was first considered in this physics paper of CochranMelech, and recently some of their results have been made rigorous and even extended. So in the complex Gaussian case, the distribution of the diagonal overlaps, so I take eigenvectors, take its inner product with itself, has been computed, as well as the expectation and variance of the off-diagonal overlaps. So this was initiated by Walters and Starr a few years ago, and then very recently Borgata and Dubach have sort of completely solved this issue. And then the work here was extended to correlation functions, so you can take multiple eigenvalues at the same time, and this was studied by Crawford and Rosenthal. And this was all done just in the complex Gaussian case. So sort of no universality has been established. It's very important that we start with complex Gaussian things. And then the only work beyond the complex Gaussian case was the real Gaussian case, where Fyodorov computed the distribution of the diagonal overlaps in both the real and complex case. There's also been some related work on general unitarily invariant ensembles, mostly in the physics literature, but I won't say anything else about that. So basically any sort of universality results in this direction are completely open and certainly very interesting. So our second motivation for looking at this trace of products of functions of random matrices comes from looking at randomly coupled differential equations. So this ODE has been very popular in theoretical neuroscience and mathematical ecology as sort of a linearization of more complicated nonlinear differential equation. So I take some vector with n entries, and each entry is just going to evolve by this differential equation. So the time derivative, well, it has a damping term just based on its own strength, and then this coupling term. So G will just be some parameter, which will tune. X is going to be a matrix, so in our case, it's going to be our random matrix, and then it's just the interaction with the other terms. And sort of the idea, I think, in mathematical biology is often they have these very large systems where it's impossible to sort of measure all of the interactions. So the idea is maybe you can just understand some statistical properties of these interactions and then model it by a random matrix, and maybe if there's any sort of universality that can tell you what's happening. So this differential equation, it's fairly simple to solve. You just take the matrix exponential and apply it to my initial conditions. And you see how you tune this parameter. Well, if it's small, this solution will decay exponentially, and if it's big, it'll exponentially grow. And if I tune it critically, you can sort of ask what will happen in that case. So that rates us to our sort of initial motivation is if I assume the initial condition is uniformly distributed on the unit sphere, well, if I average out the initial condition, then I can express the L2 norm of the solution to my differential equation exactly as the trace of, well, the matrix exponential of my matrix times the exponential of its conjugate. So exactly the sort of problem that we're looking at. So recently in the theoretical neuroscience community, this was investigated by Marti, Brunel, and Oesterreich. So they sort of based their results on the results of CochranMelech, that I'll mention again in a moment, which were sort of non-rigorous and to just the case where X was an IID matrix that I mentioned at the very beginning. So basically, the results that we can get for studying how the L2 norm of my solution evolves, we'll see that it ends up being expressed as a Bessel function times an exponential. So in particular, so the Bessel function grows exponentially, and this term is going to decay exponentially. So depending on how G is chosen, this term will dominate, or this term will dominate. And in the critical case, when G is exactly 1, from asymptotic to the Bessel function, we get that the L2 norm is going to decay polynomial with speed t to the -1/2. So this sort of result should be contrasted with what happens in the Hermitian case. So if instead I had taken this sort of differential equation and chosen X to be a Hermitian matrix, then once again you can solve it, and it'll have the same solution, but X will be equal to X star because it's a Hermitian matrix. And if you follow the same sort of analysis, we would get that the solution decays like t to the -3/2, which is a bit faster. So somehow, sort of heuristically, the non-orthogonality of the eigenvectors causes the solution to decay slower. So that's sort of the motivation and sort of the main results we're going to talk about. And what we want to consider was something a bit more general than just taking IID random matrices, especially for these biological applications. Oftentimes, they don't, all the system won't interact exactly the same with it. Certain parts will interact more strongly with other parts of the system, or maybe they just won't even interact at all. And I want some of my random matrix, some of my entries just to be 0. So what we're going to consider is what we call structured random matrices. once again, we take a large n by n matrix. Its entries will be independent with 0 mean. But now I'm going to let the variances be different. So the variance of my ij entry will be just called Sij. Furthermore, we're going to sort of, for technical reasons, assume that all moments of my random matrix are finite. Okay, so we're going to call this matrix S the variance profile, where I just take the variance of the corresponding entry, make that the entry of my matrix. And sort of all the results about what the spectrum of X looks like and the trace of f of X times g of X star will be expressed in terms of this variance profile S. Just for notational simplicity, we'll assume that the spectral radius of S is 1. And furthermore, we can't really consider completely general variance profiles. For example, if we just took my variance profile to be 1 along the diagonal and 0 everywhere else, well, this wouldn't be a very random matrix. It'd just be a diagonal matrix and sort of in the wrong regime. So in order to sort of be in a random matrix regime, we have these two assumptions on our matrix. So we're going to assume there's two constants, kappa and k, so that when I take S to this power k, all the entries in my matrix will be bounded from below by 1 over n. And the same thing for S star S. So what you should think of this condition as is if we think of S as being the adjacency matrix of some directed graph, where if an entry of S is non-zero, then I have that edge in that corresponding graph, and if it's 0, then there is no edge. And this is some sort of quantitative irreducibility of my random matrix. Sort of says that it has some sort of expansion properties, and we're sort of in a somewhat dense random matrix regime. Okay. So that's sort of the setup we're going to consider for our random matrices. So these have been sort of recently quite popular. In the Hermitian setup, they were first studied by Gerko in the 80s, and then Sholotenko in sort of a free probability setup in the 90s. And then with an eye towards application, Shakim, Louboutin, and Najim studied these. And then they're sort of basically completely understood by Aronki, Erdős, and Kruger now a few years ago. And then much more recently, the non-Hermitian case has also been of interest. First in applications. So these are some papers from neuroscience or theoretical ecology. And then, I guess, about 2 years ago, Nick Cook, Walid Hashim, Jamal Najim with myself, and then sort of at the same time, Johannes Alt, Laszlo Erdős, and Torben Kruger considered the empirical spectral measure of these random matrices X and sort of classified what their eigenvalues look like. So sort of informally, the eigenvalues of these random matrices X, well, if we consider the spectral measure, we just put the delta mass at each of their eigenvalues. It was shown sort of the informal statement is that there exists a sequence of deterministic probability measures such that our random measures become close to the deterministic measures. And the reason we have a sequence of these is we don't really assume for different levels of n that my variance profiles are coupled at all. So for every n, you choose a variance profile for all of my entries, and then as n gets larger and larger, so for every value of n, I'm going to have some deterministic measure coming from my corresponding variance profile, and as n gets large, these two are going to get closer and closer together. So these determinist measures are always going to be rotationally invariant, so just like the circular law. They won't be uniform on this corresponding disk, but they'll be supported on some disk. And the radius of this disk is actually a very simple function of S. So I just take the prone-Frobenius eigenvalue of S, so the spectral radius, take the square root of it, and my determinist measures are going to be supported on the corresponding disk. And furthermore, my density is going to be continuous between 0 and the edge. It's possible that I could have some sort of atom or blow up at 0, so it might not be continuous exactly at 0. And actually, at the edge, it's never going to be continuous. Okay, so just to give you a few examples of what the eigenvalue density of these can look like, it can be actually quite varied. So I'll show you 3 examples and some pictures. So in our first example, we'll consider a band matrix. So the middle 1/20th of my matrix, the variance of all my entries will be 1. And on the rest of my matrix, the entries will be 0. In our second example, we'll also take a banded matrix, but this time, instead of having along my band all the entries be 1, they'll be x plus y squared. So if I'm looking at entries where x and y are very small, then the corresponding matrix entry will be very small. So this will have a lot of rows that are fairly close to 0. And then for my final model, I'll take my matrix, partition it into 3 parts, and then in each block, my variance will either be 0 or 1. So where I have a J, the variance of all the entries in those matrices will be 1, and in my other cases, it'll be 0. So in the first example, here's a simulation where we just took the matrix and plotted it, and you can see it basically looks uniform on the disk, sort of like the corresponding to the circular law. Here I look at the CDF of the number of eigenvalues less than some corresponding value. Since it's rotationally symmetric, this contains all the information as well. And then sort of the main theorem I stated about what the eigenvalues look like. Well, we can sort of characterize some system of equations which might be sort of ugly to solve, but they're easy to simulate and draw pictures. And here's what happens when we draw the picture. That you can see it basically looks uniform on this disk. Okay, in our second case, where we had a lot of rows that could be 0, a large accumulation of eigenvalues near 0. You can see that the CDF of what the eigenvalues looks like, it was quite different. You can see that there's much more eigenvalues at 0. And then when we plot what the deterministic measure should look like, you can see it's very, very spiked near 0. And then for our final example, well, actually just deterministically, that matrix is going to have a lot of eigenvalues at 0. So if you look closely, you can see it's a bit sharper at 0. And then you actually have a bit of repulsion around 0, and the density is very small. So you can see that pretty clearly in the CDFs, that I have a spike at 0, and then it's very flat, and then it converges. And we see this, the deterministic picture should be this sort of bowl shape, where the spike at 0 is sort of not rendered. So any questions about what the eigenvalues look like? So in particular with these results, we have a very good idea of exactly where the eigenvalues of these random matrices will live, basically on this set with a given radius. So now I'll return to the problem that I sort of posed at the beginning of the problem, where we take f and g to be 2 analytic functions on a neighborhood of the support of the eigenvalues, which you can see we know very well now. And then with high probability, the trace of the products of these 2 random matrices will be given by this double contour interval. So gamma is just some contour that's going to encircle all the eigenvalues of my matrix X, and gamma bar is the same contour but traversed backwards. And so I have this double integral of my functions f and g against this kernel. So I take my 2 points that I'm integrating against, and then subtract off S, so the variance profile, so the matrix that contained all the information about the variances of the corresponding entries. So I take the inverse of this matrix and apply it to the vector of all ones. This gives me a new vector, and then I take the average of this vector. So this just gives me some function of z1 and z2. So my kernel is defined just by what the variance of my matrix is. So you can probably imagine that this main result is going to follow from Cauchy's integral formula, and then the main work is just going to be showing that the trace of the product of 2 resolvents is going to converge to its corresponding kernel for any z1 and z2 that are outside the support of X, a random matrix. Okay. So now I've been alluding to this result of CochranMelech. So one of their main results of their paper was they considered the Gaussian random matrices. And they showed that the expectation of the trace of the product of 2 functions converges to this quantity. So in the case that I'm IID, then my S matrix is just all 1s, and this expression here just simplifies to being z1 minus z2, z1 times z2 bar minus 1 to the negative 1. So what we did is we made their techniques rigorous, and instead of just computing the expectation, we have a high probability computation, and we can consider different variance profiles. So now I'll return to this random ODE we talked about, where you just take the time derivative of x, and the damping term, and the coupling term. So we've chosen x to always have spectral radius less than 1. So we'll consider the case where my coupling, or my parameter is less than that. So as we saw earlier, the expectation of the L2 norm of the solution is given by this trace. So if we just apply our main theorem, well, we have our function f and g, and then multiplied by the constant. So now what we're going to see is that the behavior of the L2 norm of this solution is actually going to be universal and not depend on S very strongly at all for large T. So the idea is if we take this matrix and consider the projection onto its main leading eigenvalue, which we've chosen to be at 1, well, then this expression will just be 1 minus this leading eigenvalue of 1, and then the projection onto that eigenspace. So I just take the left and right eigenvectors of S. And then Q is the projection onto the spectral complement. So now if I apply this to my kernel, so the leading order term will be given by this expression, and this integral you can actually compute exactly, and you get just exactly a Bessel function times an exponential. And this term, because of our assumptions on S, it has a spectral gap, and all the eigenvalues of S are going to be bounded away from 1. So when I do this projection and I integrate it against this term, this will be sort of exponentially small compared to this term. So for any S, assuming it has the spectral gap condition, the leading order term will just be given by this. So we get sort of universal decay of the solution to the differential equation we considered. Which is exactly the statement. The leading order comes from just this term. And then using the asymptotics of the Bessel function, if we consider the critical case where these two terms are balanced exactly, then I get this t to the minus 1/2 universal decay of the solution, this differential equation. Okay. So any questions on the result? Now I'm going to talk a little bit about the tools we use and how the proofs go. Okay. So we've already seen earlier today, a very useful tool in studying measures on the complex plane is the logarithmic potential, which is just defined by convolving this log kernel with my spectral my measure. And I can recover my measure by taking the Laplacian of this log potential. So in principle, if I know the log potential, I know everything about my measure. We also saw that the log potential is very useful in studying measures coming from the eigenvalues of matrices, because I can write the log potential as just, well, a sum of the log of the eigenvalues shifted by z. But the sum of the log is the same as taking a log of the product, and the product of the eigenvalues is exactly the determinant. And then just expanding, writing the absolute value as the square root of, well, the quantity times its adjoint, and using properties of the determinant, we have this expression. And then I just undo that step of turning a log of products into a sum of logs. So I can express the log potential as well the integral of log of x against a new measure, L of x. And the main reason this is useful is now these are now the singular values, which are just eigenvalues of a Hermitian matrix. So I've turned the problem of considered eigenvalues of non-Hermitian matrices into studying the eigenvalues of a family of Hermitian matrices. And there's a lot more tools to study Hermitian matrices, and the spectrum is much more stable, and everything is much nicer. The price we pay is now I'm considering a large family of Hermitian matrices where I'm shifting by z in every case. So in order to study the singular values of xn minus z for any fixed z, it's a bit nicer, I think, for us to consider this Hermitian matrix. So just take x minus z and then consider its transpose and put that in the lower blocks. And now I have a Hermitian matrix, and the eigenvalues of this matrix are exactly the singular values of x minus z and negative the singular values of x minus z. In order to study the eigenvalues of this matrix, we'll consider its resolvent. So I just take my matrix, and I take some complex number with positive imaginary part, and I consider this resolvent. So if I know everything about this resolvent, then I can deduce everything about the singular values. If I know the singular values, I can get the log potential, and so on. So the point is basically knowing this resolvent sort of will tell us everything about the eigenvalues. That's the first tool. And the second tool we'll use is what's called the matrix Dyson equation. And this is useful in studying the resolvents of random matrices. So the setup is I take some random matrix Z. So this can be a fairly general random matrix. What we're going to care about is that the entries have 0 mean. And then I can take some deterministic matrix, and this can also be a fairly general matrix. I'm going to want it to have positive imaginary part, but other than that, it can be sort of fairly general. And if I start with a matrix with non-zero mean, then I can just put the mean into the deterministic part. So I can sort of write my matrix like this. So I'll consider this resolvent matrix where I take Z, subtract off some deterministic matrix, and I want this deterministic matrix to have positive imaginary part, so that this resolvent will be sort of well-defined. Z will be a Hermitian matrix in this case. And this resolvent is going to approximately satisfy this equation, which is called the matrix Dyson equation. So M is some matrix, I take negative its inverse, then I apply this covariance map. So I take my matrix M, and I sandwich it with my random matrix, and then take the expectation of the entries. So what I'm doing here is basically, you compute this expectation, you're just going to have an entry from Z, and another entry from Z, and then some entry of M. So this will basically just depend on what the covariance of the entries of Z look like. And then I add on the deterministic part. And so in their optimal local law, it was shown that the solution to this matrix Dyson equation is very well approximates this resolvent matrix. And this was shown by Alt, Erdős, Kruger, and Namish. I'm building on work of Aronki, Erdős, and Kruger. Okay. So this is how we're going to study resolvents of random matrices. So now we can return to the problem that we're interested in. So our goal is to study the product of two resolvents of X and X star at two different points. So studying products of random matrices is usually can be quite messy. So what we're going to do instead of considering this product is we're going to consider this linearized matrix. So I introduce a larger matrix whose entries are all going to be linear in X or X star. And if I take the 1, 1 entry of this matrix, it's not too hard to see that it's going to be exactly this quantity. So if I sort of know everything about this matrix, then I can rededuce this information. And I have the advantage that now I'm not taking the products of anything. So the idea is I could take this matrix and then consider some sort of hermitized version of it, just like we did with the log potential, that we started with some matrix and then looked at a Hermitian version. And then derive an equation for what this corresponding block will look like using this matrix Dyson equation. But the matrix Dyson equation in this case ends up being rather complicated, and it's not so easy to sort of solve it or sort of extract any useful information. So we sort of modify this idea slightly by, instead of having just the identity matrix, I introduce a new parameter alpha. And I'm going to think of sort of everything that involves an alpha is really some sort of power series in alpha. And that I'm really just interested in, well, the linear term in alpha. So if you just differentiate with respect to alpha and set alpha equal to 0, then I'll recover this guy. So fairly trivial algebraic manipulation. But it's going to sort of simplify our lives later. Okay, so now I'm just going to introduce this matrix. So this will be sort of the linearized version of the product of two matrices I want to take. And if I take the inverse of this matrix, then I can read off the products that I'm interested in, namely this guy, as the 1, 1 entry of this. So here's the matrix once again. And just like when we computed the log potential, we'll consider some Hermitian version of this matrix. So I now have a 4n by 4n block matrix, which I call H. I take this linearized version and then its conjugate. So if I take the inverse of H, using this sort of computation again, I can read off the product of two matrices as one of I think it's the 3, 1 entry of this matrix. So I'm going to be interested in what does the inverse of H look like, and namely its blocks. In order to study that inverse, we'll consider this resolvent. So instead of just taking the inverse of H, I'll add eta, which will just be a complex number with positive imaginary part. And actually, we can just take it to be purely imaginary, so just some purely imaginary positive number, and consider this inverse, which is just sort of a regularization of the inverse of H. At some point, we can take eta to be 0. That's sort of the end of the proof, but this regularization sort of helps avoid any sort of low probability events that H is not invertible. So now I've introduced this, this resolvent, and now to understand its behavior, we consider the associated matrix Dyson equation. So as we saw earlier, these resolvents are approximated by, well, I take the inverse of my matrix, and then some deterministic part, and then some covariance part. So the deterministic part of M is given by this expression. So if we just go back, we can see that Z and Z1 is going to be on the off diagonal, and then alpha will sit right below that. So that's exactly what's here. And then I have this covariance map. So S is going to take 4x4 block matrices, and it turns out for this case, our block matrices, we just need to consider diagonal block matrices. So this will be a diagonal matrix. And for this computation, we'll sort of identify diagonal matrices with vectors. I take my 4x4 matrix with diagonal blocks. And then S is going to act by, well, I take my matrix R. So this is just sort of an arbitrary matrix made up of 4x4 blocks with diagonal blocks. And it's going to permute the entries around. And then I take S. So S was our variance profile, this matrix whose entries were given by the variances of my corresponding matrix of X. And I apply S to that vector. And that gives me a new vector, and then I reform that as a diagonal matrix. So once again, I have a block 4x4 matrix whose entries are, of each block is a diagonal matrix. So this is the equation that's going to be satisfied by this resolvent. So I sort of solve this equation, set 8 equal to 0, and then I can read off the corresponding entry. So what's very nice about this equation is if I take alpha equal to 0 in the previous equation, so just set this guy equal to 0, then this system of 4n by 4n matrices decouples into two 2n by 2n equations. And each one of these equations is only going to depend on one of the z coordinates, so either z2 or z1. And this equation is exactly going to be, well, the matrix Dyson equation that would have corresponded to this resolvent that we listed here that just depended on one z. So this was a resolvent that you needed to understand in order to understand what the eigenvalues of X looked like. So basically, at alpha equals 0, the problem is just reduced to the previous problem of figuring out what the eigenvalues look like, which was sort of solved a couple years ago. So now we want to put that all together. Okay. So recall our goal is to understand what this guy looks like, and this can be read off by our construction as looking at, well, the solution to this previous equation. And then I take the 3-1 block, so that's just sort of how we constructed things. And then I take the derivative with respect to alpha and set alpha equal to 0, and these two guys will be very close. So call the idea of taking the derivative with respect to alpha and setting equal to 0 was sort of our construction here. Okay. So this is the quantity. So if I know what this guy looks like, then I'm basically done. So then I'll take my matrix Dyson equation and you differentiate it with respect to alpha and set alpha equal to 0. So if I just differentiate this equation with respect to alpha. And with a little bit of algebraic manipulations, it's not too hard to do, but probably a little bit long to write out. Well, I can express this quantity that I want. Well, it appears once again with this covariance matrix operator acting on it. And then this is just going to be the identity matrix in the 2-4 block. So these are just deterministic guys. And then now I have the solution to my matrix Dyson equation when I set alpha equal to 0. And it's a whole line, once again, at 8 equals 0. So I've set my regularization parameter to 0. Okay. So the point is, these are the quantities that we knew from before when we computed what the eigenvalues of X looked like on their own. So I can basically deduce this product resolvent just from the information on one single resolvent. So then if you follow this computation through and use our information about in when alpha equals 0, then I get exactly that, well, the derivative of my solution at alpha equals 0 is exactly given by this diagonal matrix. Okay. So that tells me that the trace of this quantity is just going to be given by the average of this guy, which sort of in our main result for what the kernel should look like, the trace of this guy is approximated by this quantity.